Magnetic fields. Electric field lines were used to show how electric charges would exert forces on other charges. We're going to use a similar concept for magnetism. What's nice about magnetic field lines is that they're more easily seen. The above is a picture of iron filings sprinkled on a paper on top of a bar magnet. So here's the iron filings, all these little things, and this is a great demonstration if you have this in your lab and you have a bar magnet underneath a sheet of paper. And you can see all these filings are lining up in these patterns. Those align with the magnetic field. Now obviously the magnetic field is invisible, but you can see its effects certainly more directly than you could with the electric fields. The iron filings act like little bar magnets and align with the magnetic field of the large magnet. Just as if you had a little pan of water here and you put a magnetic material here, it would point to north. Same that people used to use for navigation. And now, instead of worrying about the Earth's magnetic field, we have the magnetic field due to this bar magnet. This blue line shows a magnetic field line going through the magnet and completing the loop outside the picture. And actually it would be going this way. We'll get to that. Magnetic field lines leave the North Pole, circle around, and come on back. The red line shows a complete magnetic field line in the loop. So it starts here, leaves, goes around and comes back. The field lines exit one end of the magnet, which will be the North Pole, return to the other end, and extend through the magnet, making a complete loop. Magnetic field lines are defined as leaving the North Pole of the magnet, we said on the previous slide, and that was somewhat arbitrary, but you had to choose one, and they re-enter the South Pole. The lines, the magnetic field lines, specify the direction that the North Pole of another magnet in the field will align with. And just like electric field lines, the more lines per unit area, that indicates a stronger field. And the lines that we have here, they don't seem to be in complete loops, but they are, right? They would just have to go farther out like this, and at some point they'd run off the page. The key part, all magnetic field lines form complete loops and go right through the magnet. Like electric fields, different configuration of magnets will produce interesting magnetic fields. Here we have two magnets with their north poles next to each other, and you can see how the magnetic field lines go. And that's very similar to electric field lines if you had two positive charges. However, there's a big difference. You'd have the field lines like this, and they would never come back and loop around. But here what you have is the field lines go up just like the electric field, but then comes back and loops around through the magnet. So the electric field lines, these lines just go out to infinity. With the magnet, it comes right back to the magnet. Now we have two magnets with their opposite poles next to each other. They're attracting each other, and let's see what the magnetic field loop looks like. We'll start over here. We go like this. Goes here, goes through the magnet, comes up here, then returns back to the left-hand magnet, and then there's your complete loop. Notice it doesn't have to look like an oval or a circle. Now we have a horseshoe magnet, which is a bar magnet bent in a U shape, and it looks like horseshoes that they put on horses. One end is north, one end is south. North and south poles attract, and given that the poles of the horseshoe magnet are very close together, the field is very strong between them. One way of indicating the strength of the field is the density of the lines, and you can see how they're pretty dense there. And let's just trace one path here. Magnetic field line comes out of the North Pole, goes back in, and then what's not shown in the picture, but what is actually happening, is that field line goes right up and through and then comes out again at the other side.